So this is a super quick review of everything you need to know about the work energy principle. So let's just get started with the definition of work. And so the energy is a way to view a situation that's different than, say, the momentum principle. And it turns out that it's useful in some cases, sometimes it's not useful. But if we define work to be the force, this is the best way to do it, F dot delta R, where F is the applied force and delta R is the displacement of the force. And let's look at this, and this is the dot product, so we could also write this, if you don't want to deal with those vectors, the magnitude of the force, the magnitude of the displacement times the cosine of the angle between the force and the displacement. And this also assumes that force and the displacement are constant, so in a straight line, and the force doesn't change. If it does change, then you actually have to integrate to do this, so let's just not worry about that for right now. And the work energy principle says the work is the change in energy. Now, what really matters is picking your system. So let's just do the simplest example two different ways. Here is the ground. Here's a ball, and it starts from a height h, and there's a gravitational force on it, mg. And it's going to fall down here. And it starts with the velocity v1. I'm going to leave that as a scalar, and it ends up down here as v2. So the work, if I choose my system as the ball, then the work is going to be mgh. The work done by gravity is going to be the gravitational force mg times the displacement of h, and the angle between the way it's moving and the way the force is exerted, and that's 0 degrees because they're both going in the same direction. So that's the work done. It's positive, and it would be the change in energy. In this case, the only kind of energy I have is kinetic. So this would be 1/2 mv2 squared minus 1/2 mv1 squared. So I could solve this for v2 if I wanted to. Let's just do that. So v2, all the masses cancel. It's going to be equal to 2gh plus v1 squared square rooted. Yeah. Okay, so that's the work energy principle. Now, since the gravitational force, the work done by the gravitational force actually doesn't depend on the path it takes. It could go this way, it could go this way, and actually I have a video where I show the work done by gravity along a curved path is the same as going straight, which I think is kind of fun. So since it does that, the work done by gravity, I can actually move to the other side of the equation. I can move this over here and call it a potential energy. So now if I say my system is the ball plus the earth, then I have work equals 0 because there's no external forces on my system, and that's going to be the change in kinetic energy plus the change in gravitational potential energy, where UG is mgy. Okay, so in general, a potential is negative the work done once I move it over. So mg final, yeah, so this would be a negative change in potential because it's going from here down to there. So the change in potential is negative. So that is negative, and that is actually negative mgh. So that's that. Okay. So that's your basic work energy principle. Let's see. Let's use this to talk about the electric potential energy. Oh, let me write over here. UG equals mgy. G is the gravitational field. In case you forgot, gravitational field. That's important when we get over here. So now suppose I have this situation. I have a constant electric field, and I have a positive charge Q. and I'm going to let that move a distance x. So it starts from some velocity v1 and ends up over here with the velocity v2. And if you turn the thing sideways, it looks just like the problem we just did. Okay. So now I can say the system of the charge, then the work done, there is a force on this, F. The magnitude of F is going to be Q times E. So now I can say the work done is going to be Q, that's a Q, E, X. And the force and the displacement are in the same direction. And that would be the change in kinetic energy. Now, just like before, I can move this to the other side. So I can say the electric potential energy is negative Q, E, X. The change in. Just like I did before. Okay. That's electric potential energy. So in general, if the electric field is constant for constant E, then UE is negative, no, it's just Q, E, delta R. Let's leave it like that. Okay. So that's electric potential energy. But what about electric potential? So this is where we say, what if I look at the change in energy per unit charge? Then I get delta V equals delta U over Q. So electric potential is the change in potential energy per charge. And this is going to be measured in newtons. Let's see, in volts. I'm sorry, volts. That's it. And that's what the electric potential is. So a couple of important things. It is based on energy, and energy is based on work, which uses a change in position. So really, there is no such thing as potential. There's always a change in potential. It's always a change in potential. Okay. Another important thing when we talk about potential, we're going to use electric potential to describe situations, which is really a change. Electric potential, like energy, is a scalar, not a vector. So the electric field is like the force, and it's a vector. Electric potential is not. Okay, I know that's a lot. I think it's going to make more sense when we start calculating stuff with electric potential. So I will do that in the next video.